Hello, Christine Halsey here, and we're going to look at how to find Thevenin equivalent voltage and resistance for circuits. The Thevenin theorem states that any resistive circuit or network, no matter how complex, can be represented as a voltage source in series with the source resistance, also termed Vthevenin or Thevenin. As a Thevenin series circuit with a parallel load, our first step here is to find VTH. To find VTH, we open RL and solve for the voltage drop for the parallel equivalent voltage point, which would actually be these 2 points here. I'll go back. All right. So at that point, we can solve for the voltage in the circuit. We're pretty much creating an open here at RL and putting in our voltmeter. And what voltage would it see? Would be the voltage that is dropped across R3. So we can use I equals V over RT. Here we have 5 volts and a total of 13K, which gives me 385 microamps. And then to find the Thevenin voltage, which is the equivalent of V3, we can use the voltage divider rule, and 5 volts times the proportion of R3 to the total voltage gives us a 10K to 13K ratio times 5, which gives us 3.846 volts. You can see here my meter is set up to read the voltage across R3, and it is 3.846 volts. And the next thing we want to do is find RTH. So again, we open RL, and here I would replace it with a meter set to measure the resistance across R3. Okay, in this case, the next step is to remove the supply and replace it with a wire. And once I do that, that then puts this point in parallel with this point. So R1 plus R2 is in parallel with R3. Since there's only 2 resistor values, once I combine R1 and R2 for my parallel formula, I can use 3K times 10K over 3K plus 10K. That gives me 30 meg over 13K for a R Thevenin of 2.307 kiloohms. Okay. The next step, once we have that equivalent Thevenin voltage and equivalent Thevenin resistance, is to represent them in a circuit with the load. In this case, I've introduced a 1 kiloohm load, and I hope the calculations are right. I've gone over them and over them, but I've had a headache all day, so if anything's wrong, please excuse me. I don't think so, because I came back and verified with Multisim, so we should be good here. Alright, so in this example with a 1K load, you can see my power to the load is 1.35 milliwatts. Alright, here we're looking at a 10 ohm load, and that changes our power to 27.6 microwatts. Now change the values here to show you how it affects the power at the load. And the power at the load can be at its maximum when we make RL equal to RTH. This is what's called maximum power transfer. All right, so once we set those two equal, then we solve for our power at the load, and it's 1.6 milliwatts. Now, if we go above or below this resistance, we're not going to increase, we're not going to get any more power to the load. This is the maximum power that we can get at the load. Okay, let's take a look at a few of those circuits in multisim. Here's my Thevenin voltage. It's running, and 3.846 was what we calculated. The resistance, 2.307, I think, was what we calculated. All right, now here's with my 1K load, 1.163 milliamps, 1.163 volts. And this is the same circuit with the Thevenin equivalent, although those aren't the right numbers, so I must have not rerun it. There it goes. So those match this circuit. This is the equivalent, Thevenin equivalent circuit. So I did the measurements both ways just so we could see an example of each. And they do match. And so then I could easily take this and change this load value and rerun my circuit and see how that affects my current and my voltage. Now, for maximum power transfer, we set the R Thevenin and RL equal to each other, and we have maximum power transfer. Okay. In some cases, we'll raise the voltage and lower the current. In some cases, it'll lower the current and raise the voltage, but this is where you get your maximum power. Okay. Let's look at one more example, and I'm going to let you, one second, here's the circuit. So let's say we have a series parallel circuit here. We got a 5-volt supply, and it's in series with the 5K ohm resistor. And then over here we have a series combination and another series combination, but in that series combination is our load. Okay. So what we want to first do is solve for the Thevenin voltage. In this case, what we're seeing is that because we're creating an open here, it also creates an open for the 9K, and it reduces this to a series circuit with the 5K resistor dropping a portion of the resistance and leaving it for this parallel branch. So what does this 5K leave for this 4K group? This is now a series circuit. Since this is an open, this is just a series circuit. So we can use the voltage divider rule and say that this 4K of the 9K total, 3 plus 1 plus 5, and then multiply that times the source voltage. That's our voltage divider rule. And that tells us we have 5.33 volts left here. Okay, the next thing we want to do is look for the equivalent Thevenin resistance. So we take out the supply and put in a wire, and what that leaves us with is 5K in parallel with 4K, which equals 2.222K when I combine those two parallel branches. And then that leaves this series 9K, so I add that to the 2.22K and get 11.22K. I would suggest building a couple of these circuits for the final so you can go through and pull them up in multisim as needed.